Welcome back, students, to Chemistry, Unit 7, Stoichiometry. Today we will be talking about Unit 7.3, Volume-to-Volume Stoichiometric Relationships. When it comes to gases have no attractive forces between their molecules, and because of this, gas molecules are spread out infinitely wide from one another, meaning gases are mostly empty space. The volume a gas occupies is completely dependent upon what temperature that gas is at and its pressure. At a higher temperature, gases will expand more as those gas molecules move faster and faster, and at a higher pressure, the atmosphere will push the gases closer together. So to have a standard when working with gases, a set value, we work with gases at 0 degrees Celsius or 273 Kelvin. We also work with gases near the ocean at sea level, where the pressure of the atmosphere around us we call 1 atmosphere. In Unit 8, we will focus on gases in much greater detail, but for right now, just in precursory walk through gases, we will call this standard temperature and pressure, or STP for short. If you are at standard temperature and pressure, if you are at sea level during a snowstorm, if you are at 1 atmosphere and 0 degrees Celsius, 1 mole of any gas will occupy 22.4 liters. So 22.4 liters is 1 mole of a gas as long as you're at standard temperature and pressure. So all of these balloons contain 1 mole of gas because they all have the same volume at the same temperature and pressure. They're all 1 mole. Now granted, each of these balloons has a different mass because each of these balloons is a different gas. So if I have a 2-liter bottle of air, how many moles of air do I have? Well, 2 liters, we can use our factor label method to convert from liters into moles. For every 1 mole of any gas at standard temperature and pressure, it is 22.4 liters. So 2 times 1 divided by 22, we have 0.0893 moles of gas. If we're asked to rank gases, if we know how much gas we have, we know that 1 mole of any gas is 22.4 liters. So 3/4 of a mole, if I have moles and I want to know how many liters that is, 22.4 liters is 1 mole. This is about 16.8 liters of gas. If we have a mass, we would have to change from mass into moles, and then from moles into liters. So for every 1 mole of water, there are 18 grams of water, 18 being the molar mass of water, 2 hydrogens and an oxygen. For every mole of water, there are 22.4 liters of water vapor. So if we do 5 times 22.4 divided by 18 times 1, this is roughly 6 liters of gas. Same song, second verse, when dealing with carbon dioxide. If I have grams, I need to change from grams to moles, because once I have moles, 1 mole of any gas is 22.4 liters. So the molar mass of carbon dioxide would go here. So 1 carbon plus 2 oxygens is 44, telling us that this is roughly 2.5 liters of a gas. So in terms of ranking them from most to least, it would look something like this, with the first one being the most volume of gas, and the bottom taking up the least amount of space. So converting from moles to liters and liters to moles is fairly straightforward. 1 mole of any gas occupies 22.4 liters as long as you are at 1 atmosphere and 0 degrees Celsius or 273 Kelvin. So 1.9 liters of carbonic acid is how many moles? At STP, we could set up our factor label method to cancel out liters and end with moles. For every 1 mole, there are 22.4 liters. Liters will cancel out, leaving me with the moles of carbonic acid present. So we have 0.0848 liters of carbonic acid. We could even expand this further. How much does that acid weigh? Like in example 2, it says if we have 9.3 liters of carbon dioxide, what mass is this? There is no conversion directly from liters to grams for gases, but if we know how many liters we have, that it corresponds to some number of moles. So for every 1 mole, there are 22.4 liters, and if we have moles, moles are the central unit of chemistry, we could change from moles to grams, canceling out moles, because for every 1 mole there is some number of grams, and that's where our molar mass of carbon dioxide would come in, which would be 1 carbon and 2 oxygens. So 12 plus 2 times 16 is 44. So our answer here would be 9.3 times 1 times 44 divided by 22 times 1 is 22. So our answer is 18.3 grams of carbon dioxide. Hopefully now you are able to answer your first note quiz questions for Unit 7.3. Pause the video and answer note quiz questions 1 through 6 in your packet. The SOL is fairly straightforward. It may ask you to do a volume-to-volume conversion for a gas. So if I tell you you have 9 liters of carbon dioxide and I want to know how much carbonic acid that is in liters, if I give you the balanced equation, you can do this by dividing by 22.4, multiplying by the mole to mole ratio, and then multiplying by 22.4. Since you divide and then multiply by 22.4, these are effectively the same step. They cancel each other out. So a unique shortcut arises when converting from liters of a reactant or product to liters of another reactant or product. You could simply multiply by the mole to mole ratio. So let's see one of these in action. If I have 10 liters of oxygen undergoing this reaction, how much dinitrogen pentoxide can I produce? If we set up our factor label method, 10 liters of oxygen. The first thing in our factor label method is to convert from any unit to moles, because in order to use our mole to mole ratio from the balanced equation, you must be in moles. For every 1 mole, there are 22.4 liters of a gas at standard temperature and pressure. Liters will cancel out, leaving me with moles of oxygen. Once I'm in moles, I can use the balanced chemical equation that for every 5 oxygens, there are 2 dinitrogen pentoxides, thus canceling out oxygen, leaving me with moles of dinitrogen pentoxide. Lastly, the question wants the number of liters of dinitrogen pentoxide for every 1 mole of any gas at sea level and 0 degrees Celsius. There are 22.4 liters. So moles cancel out, leaving us with liters of dinitrogen pentoxide. We will divide by 22.4, then multiply by 22.4, which is slightly redundant. So these steps cancel each other out. Mathematically, our answer is simply 10 times 2, which is 20, divided by 5, which would be 4. There are 4 liters of dinitrogen pentoxide produced by this reaction. Again, this trick only works when you are going from liters of a reactant or product to liters of another reactant or product that you can multiply by the mole to mole ratio, which, luckily enough for you, is true for the next 2 note quiz questions. You also can do page 14, so please pause the video, complete note quiz questions 7 and 8, as well as page 14 in your packet. If, however, we are not going from volume to volume, we could have what's known as a mixed stoichiometry problem, where the units are mixed. This question wants to know if you produce 100 grams of dinitrogen pentoxide, how many liters of nitrogen gas were necessary to produce it. It says it reacts with excess oxygen gas. Anytime you see the word excess, it means you have way more of it than you could possibly use. So it means ignoring the oxygen, how much nitrogen do you need to make 100 grams of dinitrogen pentoxide? This is a normal stoichiometry problem, except for now our units are mixed. We are going to go from grams to liters. So first thing, we have to change from grams to moles, canceling out grams and giving us moles of dinitrogen pentoxide. So the molar mass of dinitrogen pentoxide is going to go in our denominator here. So that's 2 nitrogens and 5 oxygens. It's 2 times 14 plus 5 times 16, or 108 grams for every 1 mole. Once we have moles of dinitrogen pentoxide, we can change from dinitrogen pentoxide to nitrogen gas. For every 2 dinitrogen pentoxides, it required 2 nitrogen molecules. So that cancels out our dinitrogen pentoxide. Lastly, this question wants to know how many liters of nitrogen gas were produced, so we will need to convert from moles to liters. For every 1 mole of any gas at standard temperature and pressure, there are 22.4 liters, thus canceling out moles, leaving me with liters of nitrogen gas, like the question asks for. Here, we are not going to divide by 22.4, so multiplying by it does not cancel it out. You cannot just skip your setup. You cannot just skip that step. So, you have to do the full out factor label method to get your answer, which in this case comes out to be 20.7 liters of nitrogen gas produced. Mixed stoichiometry problems are not very common. However, your last 2 note quiz questions in this section are a mixed stoichiometry problem. And on page 15 in your packet, you will find some more practice on mixed stoichiometry problems. The reason I'm having you practice that is because on your quiz next class, I will ask you to do a mass to volume stoichiometric problem. So on your quiz, I will give you an unbalanced chemical reaction and ask you to balance it. Then I'll have you do a mass to mass conversion like we do in Unit 7.2. After that, I'll have you do a mass to volume conversion, just like we did in this unit. You will not be able to take any of the shortcuts. Percent yield is the only thing I haven't taught you yet. Before you take your quiz, I will explain to you what percent yield is and review slightly how to do stoichiometric problems. So this will be the last thing I teach you before your quiz. It is not terribly difficult, so you will not necessarily need to study it from the packet. You do need to study and practice balancing, mass to mass conversions, and mass to volume stoichiometric problems. I will see you next time when we will take our quiz after a short lesson on percent yield.